Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's continue our module number 4, ARIMA models, autoregressive integrated moving averages. Let's look into the details. In the previous video, part 1, we talked about ARIMA models prereqs. Basically, we covered some concepts like ACF, PACF, stationarity, and differencing. And now in this video, we're going to talk about the details and how we can use and leverage those tools to come up with the right order for the ARIMA models, right? So if you haven't watched those videos or you don't have the right background, please make sure that you watch the previous lecture video and then jump into this video. All right, module 4, part 2, ARIMA models. So here's what we're going to get at the end of this module, right? This is our very own airline passenger data set. It has a clear trend and seasonality, and we're going to see how the ARIMA model, actually I'm going to show one of them or a couple of them here, is going to perform when it comes to forecasting into the future. So that's what we're going to do. So we're going to forecast it, let's say 24 months into the future. This is my test set, and obviously this is the train set, right? And so the blue line is airline passenger, and then we're going to use a couple of benchmarks. So you might think, okay, random walk is a good benchmark or our naive forecaster. So this is the orange one. And I would argue that this is not a fair benchmark because random walk with no drift is not taking into account the trend. So a better benchmark would be the green one, a random walk with drift. So we're going to use it as our benchmark. Then I will show you how the AR component and MA component are going to model your time series. Look at the red one. So this is your AR1 component, and the purple one is your MA1 component. By the end of this lecture video, hopefully you will realize that how exactly this AR component is behaving like this and MA component is behaving like this. And as you can see, the AR and MA components of ARIMA model is not enough to model some sort of seasonality or trend in the data. So in order to model the trend, we have to add this integrated component as well. So we're going to talk about the details. But if you add the integrated component, I want you to pay attention to this kind of brownish line, which is the ARIMA 111 model. And now right away, the trend is back, right? So when you're forecasting into the future, now we have the AR component, MA component, and the I component. So the trend is back. So it's forecasting better, but obviously it's missing the seasonality. And as soon as I go from ARIMA to SARIMA, adding this S stands for seasonality, it's gonna nail it. So this is how the SARIMA 110, 11112 is gonna work. So hopefully you get a high level of how these things work, but we're gonna talk about the details in the next hour in this video. Starting with components of ARIMA model. So there are 3 main components, as you can see here. I put them in different colors. The first one is AR component, which stands for autoregressive. That captures autocorrelation in the data, right? Then the next one is MA components. So MA components is going to model the error or the noise part of the data. So this is what the error component is doing. And finally, the third component, which is the I component, it stands for integrated, and that removes the non-stationarity in the data. So basically, if your data is showing some trend or seasonality, we already know that AR and MA component is not able to model it, so we have to do something to that, right? So that's the integrating component. All right, so we can easily extend this ARIMA model to something called SARIMA. S stands for seasonality. So if your data set has some seasonality, we're going to add this component to the model, call it SARIMA. And then also you might have seen people talk about SARIMA X and put this X in parentheses. This is basically extension to your SARIMA model or ARIMA model when you're adding a bunch of other features, right? So these are going to be some external features. And let me give you an example. Imagine you have a time series. And then, I don't know, that can be anything. It can be a stock price or something, right? Let's keep it simple. Say this is Apple stock price, okay? Apple stock price, and of course this is time. And then we can use ARIMA or SARIMA to model this and forecast into the future. But you might say, you know what, maybe only including lags is not enough. So maybe I want to engineer some features. Maybe I want to add some extra features. Those features in this example can be, I don't know, it can be the price of S&P 500 itself. It can be the volume. It can be the It can be the crude oil, right? So for example, or it can be many other stuff, right? So oil, sorry. Okay, many other stuffs that you might think that there's a relationship between them and the Apple stock price, and you want to add it to your forecasting model. So you can do that. If you want to make predictions in the train set and test set, or if you want to make one step ahead forecast into the future, I would say, or I would argue, yeah, go for it, right? So for example, if you want to do one step ahead forecast. Because how does that work? So you're going to say, I have all the data onto this step. I have all the data for Apple stock, S&P 500, the volume of Apple stock, the oil price, the gold price, you name it, whatever you think that's relevant to Apple stock price, right? And then you can use all that data to make a forecast for one step ahead. So that's awesome, right? So it works. But the problem is that as soon as you want to forecast multi-steps into the future, then I think using multivariate model is kind of useless, because the reason is that you have to forecast all these things into the future in order to be able to make a forecast for Apple's stock price. So then your problem is going to become from predicting or forecasting one variable into the future becomes into forecasting multiple variables into the future. So that's why I'm not super excited about talking about SARIMA X or ARIMA X models when it comes to forecasting into the future for multiple steps. So just be aware where it's coming from, but at the same time, of course, if you want to do one step ahead forecast, go ahead and feel free to do that, and you can obviously add some features to the model, and it works. For many time series, it works perfectly, and we're going to talk about some of those models later in the course. All right. Starting with the AR components, so autoregressive models. Autoregressive model is a statistical model. Basically, this is a simple multiple linear regression model. It's nothing fancy. So if you remember from your econometrics basic courses, we have, what do we have? So let's say we have y is equal to beta 0 plus beta 1 x1 plus all the way to beta k xk plus some error term, right? Or unobserved variable. So this is basically a multiple linear regression model. And now we're going to replace these features with some lag values, right? So again, we're going to use these lag variables as the predictors. So that's simple. There's nothing new here. And autoregression simply means regressing of the variable against itself, the lag value. So that's where the name autoregressive is coming from. And now let's see what are those numbers. So we saw AR1, or we can talk about AR2, AR3. What are those numbers? Where are they coming from? So for AR models, we use this letter P to show the order of the AR model, and then we call it autoregressive model of order P. And this is a functional form for that, right? So basically your YT is going to be called some constant plus phi1, and these are the Greek letters. Again, you can use anything. You can use beta, gamma, you name it. But there's this consensus out there that, for example, for AR component, we're going to stick to the Greek letter phi, right? So, and I'm going to stick to that notion as well. So phi1 yt minus 1, phi2 yt minus 2, and all the way to phi p yt minus p. So this is order p. And of course, at the end of the day, we're going to add this error term. So this error term is, we're going to make an assumption. So it's coming from a normal distribution with average 0 and variance sigma squared. So this is a big deal. This is a big assumption, because using that assumption, we're able to come up with prediction intervals for our forecast, right? So for example, if you have something like this, again, I'm just doing these plots very naively. If you have something like this and you want to forecast into the future, and maybe this is your forecast, and then you can come up with prediction intervals, right? So basically this prediction interval is coming from the fact that you made an assumption for your error terms, and now you can back out some, for some of the ARIMA models, you can back out some closed form solutions and then come up with this values for prediction intervals. We're going to talk about the details later on, but if you have watched the previous module, module 3, when I covered ETS models, we discussed this idea of having a closed form solution for prediction intervals in very details. But again, we're going to repeat those concepts for the ARIMA models as well. All right, so this is your functional form. So obviously, this is a parametric model because we're imposing a functional form, right? And now we can explore some of the AR models, right? So we're going to stick with p is equal to 1. So again, this is just some examples. If p is equal to 1, and then depending on how you pick the values for these Greek letters or parameters, you will come up with different models, right? So let's start with this. I want you to pause the video and try to answer basically these questions. So when phi1 is equal to 0 and c is equal to 0 as well, what do we get? So go ahead and put phi1 is equal to 0 and c is equal to 0. And again, this is AR1 component, so AR1 model. It means that you're looking at yt is equal to c plus phi1 yt minus 1, and that's it. Now, go ahead and replace c and phi1 with 0. What do we get? Yeah, this is your y is equal to epsilon t. What is it? This is your white noise, right? There we go. Now the second one, if phi1 is equal to 1 and your c is equal to 0, what do you get? So yt is equal to, again, c is equal to 0, phi1 is equal to 1. Yt minus 1 plus epsilon t. Do you remember what is this? Yeah, this is basically your random walk, right? Or your naive forecaster. Random walk with no drift because there is no constant. Great, let's look at the third one. When phi1 is equal to 1 and c is not equal to 0. So you get something like this. Yt is equal to c plus yt minus 1 plus epsilon t. What is it? Yeah, there you go. This is your random walk with drift. And then finally, generally speaking, we have phi is less than 0. We say if phi is less than 0, then your yt is going to oscillate around the mean. So we have something like this. You know, imagine you have a time series, and then I don't know. This is the mean, and you're going to see why. I don't want to make it super seasonal. I'm trying to come up with some random time series here, and you will see why the AR component is exactly able to model something like this. But again, if your phi is less than 0, so your yt is going to oscillate around the mean. So imagine this is a mean, and then you see that here the phi can be less than 0. All right, but typically speaking, your phi1 is basically less than 1, and you will see in the next slides that what will happen if phi is less than 1. If phi is equal to 1, again, you see you get your random walk. If phi is greater than 1, of course, your time series is exploding. So typically your phi is less than 1, and we're going to restrict it to be less than 1 to use it for autoregressive models, right? And then we're going to talk about different values of phi in the future slides. But again, this is high level how the autoregressive model works, what are the components, and depending on how you pick the parameters, you're going to end up with different models, right? In general, we call them autoregressive models. Now you know that random forest is an example of autoregressive model. Not random forest, sorry, random walk. Yeah, here's just another slide now with me removing those question marks. So we already answered these ones. Okay, now let's talk about the forecasting equation for autoregressive models in general. So I'm going to stick to a very simple version of that when the order is 1. So this is our AR1 model. So we have yt is equal to c plus phi t minus yt minus 1 and plus epsilon t, right? And then this is our forecasting equation. So we're going to say, what if you want to forecast into the future, right? So you're going to say to yt plus 1, and then you change it to yt, right? So that's what we got. And because we are saying that these forecasts, these predictions are basically telling you what happens in the next time's horizon on average. So if I take the expectation from both sides, the expected value of this epsilon t is going to be equal to 0. So this is what we get, right? So your forecast for the next day, if you're using daily prices, is going to be c plus phi yt, right? So this is your forecast for tomorrow. Okay, again, there's nothing fancy here. We're just using this formula as our forecasting equation, but obviously we get rid of the epsilon t because we don't know what is that error in the future, and of course on average they're equal to 0. Okay, now this is, let's call it horizon is equal to 1. What if you want to look into the next horizon? H is equal to 2. So what do we get? Y hat t plus 2 is equal to c plus phi. You might want to say yt plus 1. But again, this is today. You don't know what is the value for yt plus 1. So you're going to use the predicted value, right? So this is our one step ahead predictions. And then we can replace y hat t plus 1 with its value. So it's going to be c plus phi multiply, instead of y hat t plus 1, I'm going to use this equation, c plus phi yt, right? And we can simplify it and say, well, what is it? So we're going to say c plus phi c plus phi to the power of 2 yt, and then we can simplify it even further. So we get c multiply, I'm factoring in of c, 1 plus phi plus phi squared yt. Okay, so basically we wrote it down based on, let me actually use another color, some yt and then some constant and obviously something like this. Now I can expand it to time step h, right? So if you expand it to time step h, what do we get? 1 plus phi to the power of 2 all the way to the phi to the power of h minus 1. So this is where the h minus 1 is coming from, right? If h was equal to 2, we got 1 here, so here's h minus 1. And then plus phi to the power of h multiply yt. Again, this here, h was equal to 2, so that's what we get. So hopefully this makes sense. This is your forecasting equation into the future, right? And then we can use some mathematical properties. We can rewrite this series into a summation, right? So, and then this is a formula for that, right? So your y hat t plus h given information today is going to be something like this. Your c multiply a constant plus phi to the power of h and yt. Again, this is a mathematical property. And if you do, and we have to make an assumption to get that one, right? So, and the assumption is that your phi is between -1 and 1, or absolute value of phi is less than 1. Okay, so now with this formula, we can make forecasts, right? So for example, here is a synthetic data set. By the way, I'm gonna the Python notebook is available on GitHub as well. So we are creating a synthetic AR1 time series, and this is it. This is our yt is equal to c is equal to 1, phi is equal to 0.5, and plus some errors. Our error is normally distributed with average 0 and variance 1, or standard deviation 1. Okay, so and this is how it's going to look like. Okay, so this is how it's going to look like, and we want to use AR model to forecast into the future. And how do you do that? You use this formula. So for example, you say y hat t plus 1, and then you replace all those h with 1, and you get a number, right? So that's going to be your number here. Then you're using h is equal to 2, h is equal to 3, and all the way to h is equal to 20. Okay, and as you can see, this forecast with AR model is converging to a long-term value, right? And mathematically, we can calculate that. Look at that. This is starting from here, and it's converging. And it seems that as we go further into the future, there's this long-term forecast that the AR model can give us. How do we get that? So what are we doing? We're sending this h into infinity, right? So if we send h into infinity, and we know that your phi is between -1 and 1, what do we get? So I'm just using the forecasting equation. T plus h is equal to c multiply 1 minus phi to the power of h divided on my minus phi plus phi to the power of h and then yt. So I want you to think about it. What is going on here? So first of all, let's look at this part. If phi is between -1 and 1 and h is a very large number, let's say phi is 0.5 and h is 100, 200. So 0.5 to the power of 100, what do you get? Almost 0. So that's why we can get rid of this part. And then we also know that, again, this is another mathematical property at the limit, that that phi to the power of h is basically is going to go to 0. So we get something like this. C multiply 1 divided by 1 minus phi. So this is your long-term average prediction that an AR model is going to give it to you, right? So let's use the values for this synthetic data and see what we get. So the long-term average is going to be C divided by 1 minus phi. So what is your C? C is equal to 1, and 1 minus phi, 1 minus 0.5. So what do we get? So let me use another color. So we get 1 divided by 1 minus 0.5. So 1 divided by 0.5, we get 2. So that's where the number 2 is coming from. So the AR, so now you see why the AR component, when you're making forecasts into the future, is something like this. It starts from somewhere and it converges to a long-term average. And obviously this depends on the value of C and the value of phi. In the next slide, I'm going to show this synthetic data using different values of phi, I don't know, 0.1, 0.9, 0.7, and you will see how it looks. But what I want you to take away from this slide is that, look at this time series. So if you have something like this, then the AR component can model it, right? And make a forecast into the future. And as you can see, there is no trend, there is no seasonality. So that's why the AR component can only handle the time series with no trend and no seasonality. Or namely, it can handle a time series which is stationary. Do you see that? This looks very stationary to me. And we talked about the concept of a stationary the last time. So the AR component by construction is able to model something like this. It's not able to model something like this. So you cannot make a prediction using AR model for a time series like this. It's not going to perform. Okay, now let's look into those examples of simulated data with different values of C and phi. All right, this is our AR1 model. You're using 4 different values for phi, and this is what we get, right? And as you can see, it's very sensitive to phi, right? So let me actually write down the equation one more time. This is your model, yt is equal to C plus phi yt minus 1 plus some epsilon, and we assume that the epsilon is normally distributed with average 0 and variance 1. And yeah, the first one, let me use my highlighter. The first one, phi is equal to 0.1. And as you can see, this is how the data set is going to look like. And we can you forecast into the future using AR1. Then the next one is phi is equal to 0.3. And again, this is how the simulated data is going to look like. And this is how our forecast into the future is going to look like. Phi is equal to 0.7. Phi is equal to 0.9, and etc. Right? And as you can see, as this phi is increasing and your synthetic data is becoming more like random walk, especially if that phi is close to 1, right? So right now, the phi, let me actually use the cursor, is 0.9. This is a large number. And then this is the time series that's an AR model can basically model with phi is equal to 0.9, right? In the next slide, I'm going to show to you how it's going to look like when this phi is very large, close to 1, and you will get your random walk, right? Yeah, so again, just keep in mind the takeaway from these slides. I want you to just train your eyes with a time series like this. When you see something like this, that's what the AR model is able to capture, okay? Okay, here's a case where phi is equal to 0.99. So this is very close to our random walk, right? So let me write down the model one more time. Yt is equal to C plus phi yt minus 1 plus epsilon t. Okay, and now imagine this is your synthetic data, and real world data it can be something like this. The reason that I'm working with synthetic data because I want to change that phi, and you see how this time series is generated. In real world, you're going to observe one time series, and then you're going to use AR model and to basically do some optimization to figure out what is the value of phi or phi, what is the correct order, and things like that. But here's something very important I want you to pay attention. Imagine this is your data, okay? This is what you're seeing. I want you to cover everything else except this blue line. So when I show you this blue line, then you would say, how can I model this, right? As I told you in the last slide, you know that AR component is good when the data set is stationary. Here you might think that you say, okay, there's a trend here. I don't care about seasonality, but there might be a trend, right? If there's a trend, and then you can say, you know what, let's use ETS models. You can use different econometrics models as well, right? Let's do additive error term, additive damp trend, because this trend seems to me very, I don't know, exaggerated. Maybe the growth should be dampened over time. And then imagine there's no seasonality. So you can model this blue line using an ETS model. So that's one option, right? And then if I force you to use, for example, autoregressive model, you can go ahead and use this model and then throw data at it and see what are the values for C, phi, and etc., right? And again, I'm forcing you to, for example, use AR1. And if you do that, you will see your AR1 model is having a hard time because it's giving you phi is equal to 0.99. This is a very large phi, and that simply means that your AR1 model is becoming a random walk, right? Basically, if there's C, random walk with drift in this case. So we don't typically use AR model to model something like this. We have to do something to that. What is that something? We need to make it stationary. We need to detrend the data, deseasonalize the data, and then apply AR1 component to that. So that's why AR alone is not going to perform well here in this example. But regardless, if you're curious to see how it works, the red line are the predictions for your AR model. Now, as you can see, we start from some number and we are converging to that long-term average, right? Then you can calculate the value of that long-term average. It's equal to C divided by 1 minus phi. So our C here is 1, and 1 minus phi, 1 minus 0.99. What do we get? 1 divided by 0.01. And if you do the math, you get 100. Do we get 100 here? Yes. And by the way, you can go back to the previous slide and calculate those long-term averages as well. So hopefully it makes sense. All right, so again, the high level of the autoregressive model understands what kind of data set the autoregressive model is good at modeling. It's not going to be something like this, right? So I will never use an AR1 model to basically make a forecast for this blue line. Again, when I say I would never, obviously you can use the performance of the model in a test set and look at some metrics like RMSE and compare it with different models and see which one is performing better, right? So yeah, so that was it. Now let's get into the next component of ARIMA model, which is, I will talk about the moving averages component next, MA component. Now let's talk about the moving average models, right? So this is the second component of our ARIMA models, right? So here's a functional form, and as you can see, we're writing down our YT as a combination, as a weighted moving average of the previous error terms, right? So here's the current error, and then the last error, the error in the 2 periods before, and all the way errors to the Q periods before, right? So we call this model moving averages because we're using a moving average of the previous forecast errors in a regression-like model. So we call it regression-like because, again, this functional form looks very familiar to us, right? So we're putting together a bunch of features with adding some Greek letters and add them in a linear way, right? We call it regression-like because you should pay very good attention. These errors are not observable. So that's why we say, okay, so this is not quite like the usual regression in a usual sense, right? But regardless, we can write down an equation like this, right? We're going to use the letter Q to say this is the order of the moving average model. And for AR model, we use P. For MA model, we're going to use Q. Again, these are some letters or Greek letters that are commonly used, and I want you to stick to this notation as well. So if you read any textbook, everybody is sticking to this P, Q, D, and etc. for ARIMA models, right? And the idea is that you can think of this YT as a weighted moving average of the past few errors. As a matter of fact, you can even write down your AR model as an MA model, right? So for example, we know that any ARP model can be written as MA infinity, right? So let me actually write it down for AR1 model, and you can get the idea how it works. So remember, this is your AR1 model. YT is equal to C plus phi YT minus 1 plus epsilon T, right? And now, what if I replace this YT minus 1 with its value from this model, right? So what do we get? YT is equal to C plus, again, phi multiply YT minus 1. I want you to go ahead and use this formula and replace T with T minus 1. So what do we get? C plus phi YT minus 2, hopefully you're following, plus epsilon T minus 1 plus your epsilon T. Remember, just make sure that everybody is on board. Let me use your highlighter. We're replacing this with this. Okay, and now going back to the equation, what do we get? So we have something like this: C plus phi C plus phi to the power of 2 yt minus 2 plus phi epsilon t minus 1 plus epsilon t. And I can go, and I can go all the way down and then replace this yt minus 2 with its relevant components, right? And then if you keep doing it iteratively, you will see that at the end of the day, these are the terms that you have, right? So you have an epsilon t. This is going to be your epsilon t. Then you have some constant, multiply your epsilon t minus 1. So we're going to show that constant with theta 1. And then we have another one for theta 2 and all the way to theta q. So hopefully you can see that how we can go from the AR model to an MA infinity model, right? So the point is that basically, again, any time series can be thought of as a weighted moving average of the previous errors. And think about it intuitively, right? So imagine you want to forecast into the future, you have nothing. Your next forecast is a random number and it's purely error, right? And then you say that the forecast after that, it's also error. So it's going to be a combination of the previous or weighted average of the previous error. So you can think of it like that, right? And then we're going to put some restrictions. We're going to say that this theta should be less than 1 and greater than minus 1. And that simply means that the most recent observations are going to carry greater weights than those from the distance past, right? So again, we had the same assumption for AR components as well. So this is the moving average components. I know it seems a little abstract, but just bear with me. I'm going to show you some examples, simulated data, play around with these values for thetas and see how it's going to look like. Okay, before we move forward with the moving average models, I just wanted to emphasize one more time that you should not confuse this model, the moving average model, with simple moving averages or exponential weighted moving averages methods that we covered in the previous module, right? So the moving average models, these ones that we're talking about, the MAQ, let's call it MAQ. This is used for forecasting future values, right? However, our moving average methods or smoothing methods, these are the ones that we use for estimating the trend or cycles of the past values, right? So here's a simple example. Again, the mathematical operation is the same. You're talking about weighted moving averages, but weighted moving averages of what? If it is errors, this is MA models. If it is the past or lag values or your target variable, whatever it is, the level, it's going to be your exponential weighted moving average methods or simple moving averages, right? So here, look at that. So for example, this is a stock price, and these are the weighted moving averages, right? So for example, the orange one, orange-ish, it's brownish. It's 9-day simple moving averages. And then this is 21-day simple moving averages, which is using the previous observations, previous lags, right? Okay, now we can move on with the examples showing moving average models for different values of C and thetas. Okay, let's talk about the forecasting equation for moving average models. We did the exact same exercise for AR models. Now let's show how it looks for the MA model. So again, starting from a very simple MA1 model, this is what we get, the constants plus, again, Q is equal to 1. I'm including one lag value for the error term, and obviously this error term itself, which we assume that it's normally distributed with, oops, let me fix it, normally distributed with average 0 and variance sigma squared. Okay, so how does the forecasting equation look like? So we want to forecast into the future. Let's say H is equal to 1, so one step ahead forecast. So what do we get? Y hat t plus 1. This is equal to mu plus phi epsilon t, right? Again, remember, we don't need to write down the epsilon t plus 1 here, simply because we don't know what are the errors in the future, so we're going to erase it. Okay, so, and then what if h is equal to 2? If h is equal to 2, we had y hat t plus 2 is equal to mu plus phi epsilon t plus 1. What if h is equal to 3? So we get y hat t plus 3 mu plus phi epsilon t plus 2. But the problem is that, look at that, we don't know what are these error terms into the future, so we get rid of them. Okay, so your forecasting equation is going to become something like this, right? And what is this mu? Is it a random number? Obviously no, this is the average of your series. Why is it the average? Because remember, this is modeling or econometrics 101. Your predictions are going to be the expected values, right? So the expected value of so this number is going to be the expected value of your time series is going to be show up in this model as a mu, right? So now we can look at some of these moving average models. Actually I'm showing you the synthetic MA1 time series with 20 step ahead forecast. Now let's say theta is equal to this. This is theta. Let's say theta is equal to 0.5, right? So if mu is equal to 0, theta is equal to 0.5, and your error is normally distributed with average 0 and variance 1. How does the time series look like? This is how the process is going to look like. And then what is your forecast? Forecast into the future is always equal to mu. Your mu here is 0, so that's your forecast into the future. Always 0. Okay, let's play around with these thetas in the next slide and see how it's going to look like. Okay, so this is simulated data for MA1 process and for different values of theta, right? So look at that. This is if theta is equal to 0.1, how the process is going to look like. And for all these models, mu is equal to 0, so that's why your long-term average is always 0, 0, 0, right? And then if I increase theta, look at that. The theta is equal to 0.3, theta is equal to 0.7, theta is equal to 0.5. And again, just like what we did for ARIMA, for AR model, I want you to just train your brain to become familiar with what kind of time series the MA component is able to capture, right? Is able to model. So this is pretty much, again, they're roughly speaking, the magnitude is obviously different, but pretty much the same as the AR components, right? So if your data set is a stationary, so that's what I'm talking about. If your data set is a stationary, both the AR component and MA component can handle those time series, right? So far, what do we have? So we talked about this AR component, and now we're adding the MA component to the ARIMA. So let me write it down. ARIMA. And we saw that AR and MA are able to model something like this. What if I have something like this, right? What if my time series has a trend? Or what if my time series has seasonality? I don't know. And seasonality and trend. And we know that if that's the case, your data set is non-stationary, and AR and MA component alone are not enough. So that's why we need to add that third component, right? So we call it 1, 2. The third component is the integrated component. Basically, at the core of it, that component is going to take any non-stationary data set, do a simple differencing, and then make it a stationary. So that's that. We talked about the details of a stationarity last time in the previous lecture video. So if you don't have the background, please watch that lecture video first. Okay, so before I move on to the I component of ARIMA model, I want to leave you with an exercise. So far, you know what is AR and what is MA, right? So we have models, we call them ARMA. So this is ARMA model with the order of P and Q. I want you to pause the video and write down an equation for this model. For ARMA, let's say 2, 1. So pause the video and write down an equation for YT. So actually, YT. Okay, so here's the answer. So you're gonna have a constant plus, I have two components of autoregressive, so I use phi 1 yt minus 1 plus phi 2 yt minus 2 plus, then I need one component, let me use another color, of the previous error, so I got the theta 1 epsilon t minus 1, and finally we have our, let me use another color, do not confuse it, epsilon t. So this is the error in general. Okay, so that's not part of the MA component. Okay, so that's it. What we have so far is ARMA. ARMA models with order P and Q are able to model time series like this, stationary time series. Okay. So here's the third component, the I component, integrated. So we know ARIMA stands for autoregressive. integrated moving average. We talked about AR and MA. Let's talk about the integrated part. So here's a functional form, right? And now you might say that, hey, wait a second, this is just like, I see AR component, I see MA component, and where is the I component? So this is your I component. Oops, sorry, let's see. Let's use another color. Do you see your Y is prime? So this is the I component. So if I have 1 prime, it means that we are differencing 1. And this is not a standard notation, but you can say, for example, if you're double differencing, to use Y prime prime. But typically, we just use Y prime to show that, hey, this data set is difference or detrended or deseasonalized. So that's the integrated components, right? And we're going to use letter D here for the I component. So now our ARIMA model is ARIMA PDQ. So P stands for the order of autoregressive, D stands for the order of integration, and Q stands for order of moving average components, right? So again, let me actually show you. This Y prime is a difference time series, D is the degree of first difference, and then remember that these PDQs are estimated using maximum likelihood estimation. So you have this functional form, you throw data at it, you calculate the error, and then you're going to come up with the cost functions, and then you use maximum likelihood estimation to optimize the parameters. Okay, basically by minimizing that cost function. So we talked about this MLE process in module 3 in very detail. The process is exactly the same. So if you're not familiar with that, watch the previous module, but hopefully you can remember from last module that how the MLE works. The setup is pretty much the same. Use that maximum likelihood estimation to figure out what is the correct values for the parameters, right? All right, and now let me give you another exercise. I want you to pause the video and write down a model for ARIMA. Let's do 1, 2, 1. Okay, how does this look like? Okay, so hopefully you're getting something like this. Because I have 2 double differencing, I can do double prime here. And then what do I need? I need a constant, I need autoregressive component, so phi 1, y double prime t minus 1, and I need 1 component for the error as well, so theta 1 error t minus 1 plus the error in the data. Okay, so hopefully it makes sense. Now let's look at some special cases of ARIMA model. So the first one is ARIMA 000, right? So again, remember, this is your functional equation. And then now I want you to go ahead and pause the video and then see what is ARIMA 000, right? With no constant. So if I plug this c is equal to 0, and then basically no autoregressive part, no moving average part, and basically no integration, what do I get? You get yt is equal to epsilon t. What is this? Yeah, this is your white noise, exactly. Then what about ARIMA 010? So again, I want you to pause the video and think about all these things, right? So what do we have here? Because this is 1 integrated, so I have y prime. So y prime t is equal to epsilon t. Then you can write down this y prime t as yt minus 1. That's exactly what your y prime, right? So what do we get? Yt is equal to yt minus 1 plus epsilon t. What is this? We have seen this before. Yeah, if there's no constant, which is the case here, this is your white noise. It is your random walk, right? Random walk with no drift. Then we are adding a constant, so it's going to be random walk with drift. ARIMA P000, what is this? This is your autoregressive model. ARIMA 00Q, what is this? This is your moving average model. So that's where the name is coming from, right? So white noise, random walk with no drift, random walk with drift, and then autoregression and moving averages. All right, so as you can see, when you have an ARIMA architecture, you can basically model anything you want, the ones that we have discussed so far, okay? Okay, now that we know what is ARIMA, actually let me write it down. So we have ARIMA PDQ. Q. We're going to use the small letters. And then you might wonder, okay, how do I know what is the order of P, what is the order of D, what is the order of Q, right? For D, it's pretty straightforward. You're going to look into your time series. If there's trend, seasonality, you need to difference it, right? So D is equal to 1. Then again, you look at your time series again. If it becomes something like this, I don't know, then you know that AR and MA can handle it, right? So basically your data set is non-stationary, and you're going to make it stationary with one differencing, stationary. And you know that you don't need to rely on your eyes. We can use ADF test, KPSS test, and if that's stationary, we're going to stop there. Typically, we stop at D is equal to 1. So for D, it's pretty clear, right? Then how do we identify the values for P, the order for P and Q? Okay. There are some rough guidelines, and I want to give you a heads up. This is going to be a little subjective, and it relies on expert knowledge, domain expertise, and etc. But you can, at the end of the day, you can use something called, for example, Autoregressive using Python packages, and then those Autoregressive is going to do some optimization behind the scenes, some calculation, and tell you what is the best values for PDQ to give you the minimum value of your cost function, right? At the end of the day, you're minimizing a cost function. What combination of these PDQ is going to give you that? So you can basically rely on those numbers as well. But I want to give you some guidelines that if you are pretty familiar with the time series that you're working with, then maybe you want to spice it up with your domain knowledge as well. And in the Python lecture video next class, you will see what do I mean by that, because ARIMA does not necessarily get the optimal model at the end of the day. Sometimes your model is, you get a slight better performance in the test set, but your model is unnecessarily complex. And you're going to see exactly what do I mean by that if you watch the next lecture video. But again, let's start with some rough guidelines. Okay. And in order to figure out what is P and Q, we have to go back to our ACF PACF plot, right? So we start with the AR component, basically to identify what is the value of P. We're going to look at partial autocorrelation, because guys, pay very good attention to what are we doing here. This AR model is a combination of previous lags, right? So AR model is something like this. You have YT, phi1 yt minus 1 plus phi2 yt minus 2, and etc., right? You get the idea. What is this? This is a multiple regression analysis, right? How do you interpret this phi1? The marginal effect of yt minus 1 on yt. How do you interpret phi2? The net effect, the marginal effect of yt minus 2 on yt. So that's why we're interested. If you want to figure out what is the correct value of order P, you have to look at partial autocorrelation, right? So, and then imagine this is how your partial autocorrelation is going to look like. With that, we're going to use this, again, rough rule of thumb. Okay, we know that identification of AR model is based on PACF. We know the rationale behind it. And then the P is said to be the maximum significant non-zero lag in PACF, typically followed by a sharp decline. Okay, so just ignore lag is equal to 0 because it's always equal, partial autocorrelation is equal to 1. Let's start from here. So this is if P is equal to 1, P is equal to 2, and etc., right? So do you see a sharp decline after P is equal to 1? I would say yeah, but again, just look at the absolute value. There's a decline. We go from 60% to 40%, so you can think of it as a sharp. So I'm thinking of some candidates for P. So P can be 1, it's okay. And then how about 2? For sure, because after 2, we go from this number to almost 0 here, right? So 2 is a good candidate as well. Then how about 3? No, because after that there's an increase, not a decline, again, in terms of absolute value. How about 4? Yeah, is it 4 or 5? So 1, 2, 3, 4, 5. Actually, sorry, this is 1, 2, 3, 4, 5. So from 3 to 4, no. From 4 to 5, no. How about 5? Yeah, because after 5, there's a sharp decline. So my better candidates are something like this, right? So P is equal to 1, 2, 5. And obviously, when P is equal to 1, your model is simplest. When P is equal to 5, your model is most complex. So if I want to manually engineer the order of my ARIMA model, I will consider p is equal to 1 and in this case maybe 2 and 5, right? Because after 1 there's not a sharp decline, right? So again, but you can try all the 3 and see which one is giving you the best performance in the test set, right? So that was the AR components. We have the same rule of thumb for MA component. For MA components, we're going to use ACF, autocorrelation, not the PACF, and then we're going to use the same technique. We say Q is set to be the maximum significant non-zero lag in ACF followed by a sharp decline. So again, ignore the first one. Then what are the good candidates for my Q? So this is 1, 2. From 1 to 2, I don't see a sharp decline, right? Again, but 2 to 3, there's a clear sharp decline. So you can think of 1 and 2, but I would be more leaning toward 2, if that makes sense, right? Because again, there's a sharp decline after 2. So maybe how many combinations we have here? So we have 3 here, 2 here. So maybe I have a good, I don't know, 6 candidates for my ARIMA. I can play around with them and then see which one is performing best in the test set. This is exactly, and again, you narrow down all those combinations to 6 here. If you use ARIMA is going to look into a bunch of more combinations. I don't know, 20, 30, depending on the Python package and what default values for these orders the package is using. But behind the scene is looking into 20, 30 different combination and give you the best. But again, if you are an expert, if you have a domain knowledge with that data set, so probably you're going to say, you know what, maybe I will, overall, by looking at these two, I will say maybe I need an ARIMA. And imagine I have made this data set stationary, so there's going to be 1 here. And then I'm going to pick p is equal to 2 and q is equal to 2. So maybe this is my winner. Okay. Okay, model selection. So how can we do this process more systematically? And what is happening behind the scene, right? So this is, again, we have ARIMA, P, D, Q. I mean, when we say model selection, it means that what values of P and D and Q we should have, right? So we can use either information criteria or any cross-validated performance metrics like R-square. I'm not a big fan for time series. We talked about all the details in previous modules. Mostly RMSE and MSE is my favorite ones. Because again, MAPE and SMAPE can be exaggerated if your target values are close to 0 or if they include 0. So they can be inflated. So let's say RMSE. Okay. You can use cross-validated. So for example, you can say, hey, for ARIMA, I don't know, 1, 1, 1, we have a RMSE in a cross-validation. It's a number. ARIMA 2, 1, I don't know, again, 1. Here's another RMSE cross-validated. And whichever gives you the lowest one, it's going to be your winning model, right? So we can do it either that way or use information criteria. So what are those information criteria? So we have AIC, AIC corrected, and BIC. So I think we have spent almost more than half hour in module 3 explaining all these metrics and how the maximum likelihood estimation is working behind the scene to figure out what is the optimal value of model parameter in general. So I'm not going to repeat myself here again. So if you're interested, please watch the previous lecture videos from module 3 when I talk about the model selection of ETS. So model selection, ARIMA, the process is pretty much the same, right? So at the end of the day, there's a likelihood function. You're trying to maximize that likelihood function or minimize the negative version of that. So that's why we're interested in minimum value for any of these things, right? And then there's this parameter K. Basically, you're penalizing this this function by saying that if you make the model more complex, i.e. if you increase K, then you're penalizing the model, right? So there's a trade-off between having a more complex model and having better predictions, right? So again, the more complex model obviously is going to perform better in the train set, but in the test set we have to see if it is overfitting or not, right? So what is this K? K is the number of parameters. So for example, if I have ARIMA 1, 1, let's see, Let's for this one, ARIMA 1, 1, 1. The parameters are basically we have one phi 1, one theta 1, and then most importantly your sigma square. So this is very subtle. Again, we spent almost an hour in the previous videos talking about the advantage of econometric model is that you're gonna estimate this forecast errors specifically, right? So, and that was coming from the fact that you say your errors are normally distributed. We said, okay, errors are normally distributed. With that fact, when I use maximum likelihood estimation, I can estimate this sigma square. And this is good because this will help me to come up with prediction intervals, right? So that's what gave us some closed form solution for prediction intervals, right? And either using ETS models or ARIMA models. So that's why when you're using PyCaret or ScaTime or any other Python packages when you're doing time series forecasting, if you use econometric models, you can, by construction, have prediction intervals, right? So that's why when we set that prediction interval is equal to true, the model is able to generate those confidence intervals for you, 90%, 95%, whatever. Let's call them prediction intervals, okay? All right, so yeah, I think this is the model selection process. And I would say you can automate this entire process using ARIMA in Python, or you can say, hey, I'm an expert. I have worked with this data set for years, and I'm going to look into ACF plot, and I'm going to figure out the orders myself. And I'm going to keep it as simple as possible because the simpler the model, the more explainable it is, and then you don't need to make it unnecessarily complex. Again, next time you're going to see exactly what I mean when we cover the Python part. Okay, so here's a quick whiteboard for those who are interested in the details of ARIMA model parameter estimation. I make it optional and I keep it very brief. Again, we talked about the details in the previous module. The process is pretty much the same. So let's go with a very simple ARIMA model. So I'm going to say, again, I'm going to keep it simple to make it manageable. So say ARIMA 101, right? So how do you write this model? So it's YT. This is not Y prime because the integration is 0. So yt is equal to a constant plus we have one lag term, we have one lag of error term, and we have our error term. Okay, so then I can go ahead and rewrite this equation in terms of my error epsilon. So what do we get? It's going to be yt minus c minus phi yt minus 1 minus theta epsilon t minus 1. Okay, so these are the errors. And then we're going to make an assumption here. We assume that those errors are normally distributed with average 0 and a standard deviation or variance sigma square. This is a big assumption. We talk about it, but if you make this assumption, it's going to allow you to have a sense of the distribution of your epsilons, right? So this is the distribution of your epsilon. It's normally distributed. And with that, we can say, go ahead and calculate the likelihood that these errors are coming from this distribution under these parameters. Hopefully this makes sense. Again, I apologize if it is too fast, but again, we have talked about the details in the previous module. So now I have a function, there's a functional form for the density of this normal distribution. So I'm going to use that one, right? So we say the joint probability or the likelihood is multiplication of a bunch of probabilities. What are those things? 1 divided by 2 pi sigma square. So this is I just want to make sure that maybe this is a multiplication operation. It's not pi. So this is pi, that's multiplication operation. Okay, because we're calculating the joint probability, right? Basically multiplying a bunch of those probabilities, and then e to the power of your minus epsilon t to the power of 2. So this is nothing fancy. This is the formula for density function of the normal distribution. So I have the likelihood. I can work with maximizing the log version of that likelihood over the model parameters. The parameters are c in this example, phi, theta, and now most excitingly sigma square. Okay. So there you go. So we use this optimization, and this is what's happening behind the scene when you're doing Python packages, and these are the parameters of the models that are going to be identified using this maximum likelihood estimation. Okay, cool. Okay, now we know all the details about ARIMA model. The rest of the slides are pretty straightforward. We just want to extend them to, SARIMA model, include seasonality, right? So again, this is an extension of ARIMA. Now we're including additional seasonal terms, right? So it is used to model time series that show seasonal pattern. Now we're adding 4 more letters. So let's actually write it down. This small letter PDQ, these are our non-seasonal part of the model, and capital letter PDQ are the seasonal components of the model, and then M is simply your period of seasonality. It can be 4 for quarterly data, 12 for monthly data, right? And so what is capital letter P? This is the order of seasonal autoregressive components. D is the degree of seasonal differencing, and Q is the order of seasonal moving average component. This is pretty straightforward. I don't want you to overthink it. Let me actually show you an example, and hopefully it makes sense. So imagine we have this ARIMA, and I'm going to go with 101. Keep it 100. Keep it very simple. So what is it? YT is equal to a constant plus phi1 yt minus 1 plus error. Okay. Now, if I want to extend it to SARIMA, again, I'm going to work with the simplest one, but you should get the idea. So SARIMA and then capital letter P. Let's use another one, and then let's keep it simple. Okay. And yeah, we're adding seasonal components. And imagine your data set is monthly. Okay. So then here I need to add another autoregressive component. Let's call it phi2. And this is yt minus what? Obviously, it's not yt minus 2. This is a seasonal component. And we go 1 year back if it is monthly data, right? And it should make sense. Let me show it visually here. So imagine there is, and just for the sake of argument, we can say the data set is seasonal as well. So I can call this 1, and I can say these are deseasonalized data sets. I use S at the top. You get the idea. This YS is your YT minus M. Again, I'm playing around with these models. It should be pretty straightforward. And now I have only seasonal components. I don't have trend component. Let's say I have something like this. Again, I wish the data set was like this, but this is pretty straightforward, right? This is a simple example. Imagine, for whatever reason, whatever data set it is, this is your December data, right? And then you want to forecast into the future. You want to forecast for January. If you want to forecast for January, you might say that, you know what? Yes, YT minus 1 is important. Your YT minus 1 is December. But I'm interested in YT minus 12 as well, which is going to be your previous January. That's what we're doing by adding this S components, right? Not only the one lag matters, the previous lag of the previous season also matters. So that's what makes it SARIMA. You can have the same argument for the MA components, the MA of the seasonality components, and etc., right? Actually, as a matter of fact, let me leave you with an exercise. So I want you to write down the functional form for SARIMA. 1 1 1 1 1 1 12. Okay, I want you to pause the video and think about it. Okay, so here's a quick answer. So this is my YT, and I'm going to put a prime, and I'm going to define this prime for you. So this I can do double prime, whatever. So the first prime is this. Y prime is equal YT minus 1. The second prime is this. I'm seasonal differencing, right? So let's say Y seasonal is YT minus 12. And then Y prime prime simply says that this is double differencing. First, or you can do it, it really doesn't matter. You can deseasonalize it first and then detrend it. So this is deseasonalized component, this is a detrend component, right? So there you go. That's your y prime prime t is equal to, we have a constant, we have phi 1 y prime prime t minus 1 plus theta 1 epsilon t minus 1 plus, so this is the non-seasonal component. Let's add the seasonal component. Phi 2 y prime prime t minus 12 plus theta 2 epsilon t minus 12 and plus your error term. So hopefully you can connect the dots and see how beautifully this SARIMA model is able to speak to different components, non-seasonal components, seasonal components, and etc. Okay, now let's look into an example and try to connect the dots and put everything together that we learned so far. So what are we interested in? We are interested in SARIMA, and then small letter P, D, Q, capital letter P, D, Q, and then some seasonality period. So here we're working with monthly US leisure and hospitality employment between 2001 and 2019. So your M is going to be 12. You're working with monthly data, and these are the number of people in terms of millions, right? Just look at this data set. What can you do, right? So far, whatever you learned in this course, you say, hey, this is, if I want to do econometric, this is a screaming for a good ETS model, right? I can do additive error, again, I can add a trend, and then maybe additive, say seasonality. Seasonality can be additive or multiplicative. We can think of it as additive, right? So it can be my ETS model. So I can do it that way. Now we have ARIMA, right? So I know that AR components and MA components cannot handle something like this because this is clearly non-stationary. So that's why we have to add that integrated components as well, right? So this data set is showing trend and seasonality. So this means that I need to detrend it using d is equal to 1. I need to deseasonalize it using capital letter d is equal to 1. Hopefully you're following. If I do that, my data set is going to transfer from something like this to something a lot more, I don't know, predictable with MA, and so maybe something like this. I don't know. I'm just speculating. We will see how it happens, what it happens. It shouldn't be, there's no seasonality, so maybe I should do something like this. Again, there's no seasonality, okay? So then when we get to this part, the MA and AR components are going to take it from there, okay? So that's very beautiful. I hope that you're appreciating the beauty of SARIMA models, right? And so then first we're going to deseasonalize it, then we're going to detrend it, and then we figure out what is the right order for P and Q and capital letter P and Q. So that's the plan. You can also look at the ACF of the original time series. It's telling you that there is seasonality, there is trend because it's diminishing, and etc. So you have seen all these things before, and hopefully now you realize why we need to start this module with reviewing the ACF, PACF. Okay. All right, so this is we start with d is equal to 1, deseasonalize the data, right? So this is your YST. Again, I use it for deseasonalizing, which is YT minus M, in this case 12. So if you do that, so you will get something like this. Then I'm going to look at ACF, PACF plot. So look at the PACF. Guys, remember, we are focusing on the seasonal components now, seasonal components. So that means that we are interested in capital letter P, capital letter D, capital letter Q. This was clear. We use 1. And then let's look at P and Q. For P, I'm going to look into PACF. And this is P is equal to 1. It's not 1, it's I don't know, 0.9 something, right? So when P is equal to 1, we get this autocorrelation, 0.9 something. And then there's a sharp decline. So yeah, capital letter P is equal to 1. It's a very good candidate. And yep, I can say, yeah, this is a good one. And then I'll stick to that one, okay? How about capital letter Q? So for capital letter Q, you see that it's inconclusive here. So you have ACF, it's decreasing, so we don't know it yet. So we need to work with detrended data and to figure it out. Again, guys, this might be subjective, but if you're an expert, if you have domain expertise, domain knowledge, then you might want to say that let's start with my very own simple model. Then I'm going to use AutoRima and Python, and that Python package is going to give me the best combination, right? So let's move on to the detrending part. So this was the deseasonalizing part. So we say that P is equal to 1. It's a good candidate. Q, we don't know it yet. Let's see if we detrend it, we can make a decision. Okay, so here is the double difference, and double difference is my y prime prime. Remember, we use this ys for deseasonalizing and y prime for detrending. So y prime is yt minus 1. Okay, so this time series is deseasonalized and detrended. So that's why I call it double difference. Do not confuse this double with double simple differencing. So it's, again, detrend. Let me actually write it. Detrend plus deseasonalize. So that's what we mean by double differencing. Okay, so now look at the time series. Look at this deseasonalized, detrended time series. This is something that the MA and AR components can handle. Do you remember that? This is what I wanted you to remember. Okay, so now I'm going to look at the PACF and ACF plots out of this to figure out what is the small values of P and Q. Okay, so for P, what are my better candidates? So I can think of, this is 1, 2. There's no sharp decline from 1 to 2, but from 2 to 3, there's a sharp decline. So P is equal to 2 is a very good candidate for me. And guys, look at that. Your P, when I look at P is equal to 12 and 24 and 36, these are large. So this is confirming that our capital letter P should be equal to 1. Does that make sense? Okay. Yeah, so that was for P. How about small letter q and capital letter Q? So again, Q is equal to 1, Q is equal to 2, lag 2. There's a sharp decline here, so 2 is a good candidate. Now I want to say, look at that. At this 12, I see again a large number, right? So maybe, again, from the previous slide, it was inconclusive, but now when I see large at lag 12, I would say maybe this is Q is equal to 1 is also a good candidate, right? So here, the same story we had for capital letter P. So if this was also large and significant, I would say P is equal, capital letter P is equal to 2 or 3. But again, combining this one with the previous PACF, this is suggesting that these are good candidates. Again, these are good candidates. I can write down the model now like this. So this is my SARIMA. What do we have? A small letter P1. What do we decide for Q2? And then capital letter P1. We deseasonalize it as well. 1. And capital letter Q1, 12. So this is my takeaway by looking at the ACF, PACF for detrended, deseasonalized data and deseasonalized data, right? And now, again, if you think that this is too subjective, you can use Python, ARIMA model, and then that thing is gonna run a horse race between different values of these things and then give you the winner, and the winner is the one that is minimizing your AIC for different values of parameters, okay? Okay, so my winning model was what? We said our winning was 2, 1, 2, and then 1, 1, 1. But when we run AutoSARIMA, using Python, it seems that this is the winning model. It's pretty close to what we had, except this one is different. So again, it is looking at different combination, and it seems that this model is the winning in terms of producing the smallest RMSE in the test set. So that can be the criteria. We can look at AIC as well, or again, corrected AIC or BIC. You get the idea. Yeah. And now at the end of the day, let's say this is a winning model. I'm going to plot the residual for that winning model. And hopefully that residual, there's nothing left to be explained by the model. So remember, in the modeling section, it says that we love to see this residual to be white noise or to be super stationary. And if you look at ACF, PACF plot, there should be nothing there. And that seems to be the case for this example. And it seems that your SARIMA 210-111-12 is doing its job. All right, I think that's everything I wanted to cover in terms of model estimation, talking about the details of SARIMA and etc. I think we're done. And now in the next slide, we talk about forecasting and wrap up this relatively longer lecture video. All right, so we figured out what is a winning model, winning SARIMA model for this data set, US employment, leisure and hospitality section. And then we can make some forecasts with that. And remember, guys, look at that. This is a forecast into the future. And the beauty of it is that we can do prediction intervals as well. So here in this case, we're showing 80% and 95%. And how do we get that? Because this whole story started from the fact that you made an assumption your errors are normally distributed. And then with that, you estimated using MLE, you estimated this thing using MLE, and you recursively came up with a formula for basically your forecast errors, and then you use those ones to come up with prediction intervals. So the reason that I'm not going to discuss those formulas because it is a lot more complicated than ETS models, and computationally there's no closed form solution. There's no closed form solution for all of them, but when you do Python is not going to use closed form solution for prediction intervals. It's basically using some recursive calculations. So that's why I will not talk about the details. It's beyond the scope of this course, and honestly, there's not much value there. As long as you know where this prediction is coming from, I think I'm good with that. All right, so as you can see, the forecast is capturing the seasonal components pretty well. It's appreciating the trend and cycle components, and it's doing a decent job. So our model is working. Okay, now going back to the very first slide that we started this lecture video. So this should make a lot more sense now. Just give you a heads up, I created this chart by PyCaret, and when you're using multiple models in the PyCaret, when they do forecasts, it doesn't show the prediction intervals. But if you do them individually, you will see the prediction intervals. Because I assume that the model by default does not generate those prediction intervals if you have multiple models, because the prediction intervals are gonna get laid over it and then get a little hard to read. Okay, so now this should make perfect sense now. This is your airline passenger data set. There's trend, there's seasonality. AR1 is not gonna work, MA1 is not gonna work, you see that? And now you know why AR1 is behaving like this, why MA1 is behaving like this. And then ARIMA is gonna work considering the trend, but missing the seasonality. SARIMA is the final one that works. Okay, hopefully now you can interpret these numbers 110, 11112. All right, so that was pretty much it. And then just bear with me for 5 to 10 more minutes when I talk about why we should go beyond these econometrics models, right? I'm gonna wrap up this video by comparing ARIMA and ETS, and then finally creating this segue to why we should go beyond econometric, why we should do machine learning. Okay, ARIMA versus ETS. So we can use these models together to enhance forecasting accuracy. Actually, they're gonna model your time series from different angles, right? First of all, both of these ones are econometric based models. They are decomposition based models, right? So ARIMA is gonna focus on autocorrelation in the data, and it's going to put them together as a linear function, right? As a linear function of the past values. This is the AR components of the past errors. This is the MA components. And of course, if we need to make it stationary, that's the I components, right? However, ETS is doing it from another angle. Say, hey, let's go ahead and decompose the data set into error, trend, and seasonality, and then let's put them together in different ways, right? Additive, multiplicative, and you name it. So that's why I want you to think of this ARIMA and ETS. They can complement each other. And these are econometric ones, which means that they are we are going to assume some functional form. So you already saw lots of those functional forms in the previous couple of modules. And basically, the rest is you as a modeler decide which one performs best for your data set. Okay, so here's another slide comparing ARIMA versus ETS. I just want you to remember that we can connect. There's some overlap between a bunch of these models, right? So for example, let me actually write down the ETS models one more time. So ETS, we could have additive error, multiplicative error, we could have no trend, additive damp trend, or for seasonality, we could have no seasonality, additive seasonality, multiplicative seasonality. So we had 2 by 3 by 3. So we had 18 different combinations, right, of ETS models. What about ARIMA or SARIMA? So SARIMA, PDQ, PDQ, and you can see we can have gazillions of these combinations, right? Infinite number of those combinations. So, and we can actually mathematically go back and forth between ETS and ARIMA for 6 of those fully additive models. So 6 of these additive ARIMA models can be, so if you have additive error and then additive trend, and then yeah, 6 of those models, there's an overlap between ETS and ARIMA. Okay. So hopefully these make sense. So this is, I'm copying from the textbook. So if you're curious, you can go ahead and read it on your own, but it should be pretty straightforward. So we have, for example, 9 ETS models with multiplicative errors, right? We have 3 ETS models with additive errors and multiplicative seasonalities, and 6 of those fully additive models are, we can just write them in terms of ARIMA models. So we can go back and forth between the two, and the rest of the ARIMA models are basically the AR components modeling autocorrelation, MA components modeling the moving averages, and then we have lots of those models. All right, so the last slides on comparing ARIMA versus ETS, let's actually look into that one. So as I said, they can be used together to enhance forecasting accuracy. We use ARIMA. Let's talk about data characteristic. This is important actually. ARIMA is well suited for time series that can be made stationary, because remember that I component needs to make your time series stationary, otherwise AR and MA components cannot handle it, right? ETS, it's going to perform best when your time series is showing clear trend and seasonality. Guys, at the end of the day, if you have something like this, don't waste your time, just use ETS and then move forward, right? And yeah, and in summary, ARIMA ETS models are complementary because they offer different approaches to modeling and forecasting time series, each with its own advantages and disadvantages. And of course, at the end of the day, the choice between the two, that goes back to the characteristic of the time series that you're dealing with and your forecasting goals, right? If you want to keep your model super simple and interpretable, or more interpretable relatively, you can go with, I don't know, ARIMA, very low orders, or simple ETS, because again, ETS is pretty interpretable. You see, hey, this is a trend component, this is a seasonal component, let's add them together. So this is how it's done. Yeah, and one last slide is why we should go beyond this. Why, guys, remember we are done with the econometrics section of the course. And now I want to give you the motivation why we should go beyond that, why we should do ML, DL for time series forecasting. It all goes back to the nature of your time series. If there is strong nonlinearity in the data, then econometrics models by constructions are limited, right? So how do we fix that? So imagine, I don't know, you have something like this, and then the nonlinearity is increasing, the magnitude is increasing. What can you do? Your step 1, you can do data transformation. This is regardless of what kind of model you use. Is it ML, DL, econometrics? You can use data transformation to control this variance, right? So if I go from this on the left, let's say this is Y, to log Y, right away, or I can do Box-Cox transformation. Right away, I can tame that magnitude increase in variance, right? And then I'm going to say, hey, use ARIMA or ETS to model this one. So that's one way, right? But sometimes the nonlinearities are not this mild, right? So I call this one a mild nonlinearity in the data set, right? So your econometric models, ARIMA and ETS, can handle these mild, that's why I highlighted here, nonlinear relationships. So how does ARIMA do it? ARIMA is going to approximate those nonlinearities using multiple AR components and multiple MA terms, right? How does ETS do it? ETS does it by adding multiplicative or additive components to the model to add some flexibility to handle nonlinearity, right? So remember, I think in the ETS module, we also showed that, for example, if this is increasing, why don't you add multiplicative seasonality to handle that, right? But the problem is that if you go beyond that, if your dataset is showing some strange nonlinear pattern, then ETS, ARIMA, Econometrics by constructions is limited. It cannot handle that strong nonlinearity. So what is the answer? If you want to capture some sort of complex nonlinearity in the data, we need to transition to more non-parametric models. Remember, econometric, these are parametric models. You assume a functional form, but the machine learning, DL, deep learning, the ones that we cover in this course are all non-parametric, because look at that. For machine learning, we look in tree-based methods like random forest, gradient boosting, XGBoost, cat boost, light GBM, you name it, or neural networks. These are non-parametric, meaning that inherently they're designed to capture complex and nonlinear patterns in the data, right? So again, it all goes back to what kind of time series data set you're dealing with, and then you can decide which model to use. You want to, what matters most to you? Is it only forecasting accuracy, or you want to interpret it as well? So this goes back to our module 1 when we compared econometrics versus machine learning versus deep learning at a very high level. All right, so this wraps it up. Let's conclude this module. All right, we are done with the econometrics section of the course. We covered the ETS and ARIMA family of models, and is it only limited to these ones? Of course not. But I think you're in a place that you can handle the rest of the econometrics models doing self-study, because at the core of all of them, you're doing something related to autoregression or decomposing the time series, right? So for example, let me just give you an example. One of the other interesting econometric models is called TBATS. And that stands for trigonometrics. So let me see if I can spell it. Trigonometrics. Trigonometrics, Box-Cox transformation, ARIMA errors, trend, seasonality, right? So look at that. You know what is trend. You know what is seasonality. You know what is ARIMA. And then what if the errors are not necessarily normally? What if you want to model the error themselves? So you model them with ARIMA model, right? And then this is a trigonometric seasonal components. And this is an interesting model that now with knowing ETS and ARIMA, you can self-study it, right? So just to give you a heads up, you remember either when we were using ETS or ARIMA, our seasonality was very, very simple. We said, okay, quarterly, m is equal to 4. Monthly, m is equal to 12. What if you want to work with some seasonalities are not that straightforward, right? So what if you want to have daily seasonality, things like that, right? So that's why this trigonometrics is going to decompose the seasonalities into sine, cosine, no sine, cosine, and etc., and then put them together for modeling your, let's say, kind of irregular or abnormal seasonality, right? So again, but the whole point is that you should feel confident after covering module 3 and 4 in terms of expanding your knowledge to do more when it comes to econometrics models. So again, I specifically talk about TBATS because this is one of the more popular models when it comes to modeling seasonalities as well. But again, this is nothing fancy. It's combining ETS and ARIMA and your transformation and everything you know so far. Cool, that was pretty much it. Next time, we're going to talk about machine learning time series, which is super exciting. And it has very, very detailed when it comes to handling challenges for time series when we're doing machine learning. Until the next one, take a very good care, and I'll see you next time. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.